Yes, please.
Hi everyone, my name is Shreyas and this is Bramsh and Kenneth, they are my teammates, and we'll be working on the X0net for the class project. Today we'll be covering the background, the project flow, testing and deliverables of the project. So first starting with the motivation, CNNs are very commonly used these days for object detection, classification, and they were invented somewhere in the 1980s by Fukushima in a neocogniton paper. And in 1998, Likon made it work, and since then they have gained a lot of traction. But the problem with modern CNNs is that they work on GPUs, which are heavily multi-threaded and require a lot of compute power. And we need them to work on smaller devices and basically low power devices. So we did a little bit of reading on how that is done. And basically, there are two types of quantizations that can be done to reduce the compute power of CNNs. One is a conservative quantization, and the second is aggressive. So, so whenever we compute weights and activations in normal CNNs using any high-level programming language, we make use of float32 as a standard to represent the values. But like over the past few years, there have been a lot of like research papers saying that we don't need all these, and therefore they try to do network compression, they try to do dropouts where they reduce the number of neurons. Another school of thought has been to reduce the compute by using like quantization as a way of regularizing the network, since we do not really need to we do not need the float32. So in conservative, basically they try to scale the parameter, scale the representation dynamically at runtime, or they can be done offline. So for weights, it is fairly simple to do because you can do it offline. Like once the network is trained, then you reduce it to an int 8. But for activations, it's harder to do. For aggressive neural networks, for aggressive quantization, there are different approaches that people have taken. One is to use a bounded function for the activation. Like ReLU is the most common one, but it is unbounded and causes some issues. Another approach has been to learn the clipping value of how to quantize the weights and the activations. And the last one is to use wider layers with multiple binary convolutions. And that eventually has like one form of this is like aggressive quantization is binarized neural networks. So there have been like different papers and different approaches, but the idea is to use a binary representation to for the weight functions and the activation functions, basically everything, to compress the network in such a way that they can run on low power devices. There have been like the evolution I have mapped like of the binarized neural networks has been like there have been three main papers. One is the binary connect, which came out in 2015, where they binarized only the weights. The second was binary net, which came out in Feb 2016, where they binarized the weights and the activations. And then the last one is the X0 net, where they binarized basically everything. And now Bramsh will continue and...
Okay, can you go back to Shreyas? Okay, good.
And so there has been a paper that came out in November 2018, where they defined a workflow of how you can use quantization to develop better neural network architectures, or rather, how do you really design such networks? And they called it the Ristretto framework. But basically, what you do is you reduce or expand the layers of your neural network in an iterative fashion. And yeah, sorry, now my friend Bramsh will continue.
So the main motivation is to convert weights into the binary or even the input. So the function that we are going to use is sign x, where if the input value is greater or equal to 0, it will be assigned +1, otherwise -1. So in binary network, what they do is they only binarize the weight, and then there is a scalar value alpha, which is the absolute average over the values of weight. And for the main motivation behind it is to not use the convolution function, because in convolution function we need shift and dot product, and that takes a lot of time. So in this version they use addition and subtraction to do convolution. And in the XNOR net, what we do is we take the sign of input as well, and it's the weight. So now we can approximate the convolution using XNOR and bit count, which speeds up the factor of 58, and we use less many. So the first one shows how to convert the weight into binary, and there's a second one where we can use all the tensors to do the convert the input into binary, but then it is like redundant because some tensor will overlap. So then we use the addition way, where we take the average over the input in one channel, and then we convolve it with small k. So this is actual convolution function, where k will give us the beta, which will be the same. And we also have the alpha, like in the previous slide, for so in this way we can use XNOR and bit count instead of convolution. So this is just to summarize it. It is different binary weight connected and bit count. And we plan to implement in VHDL and in Python as well to compare the both implementations, their pros and cons, and we hope that VHDL will be faster than Python, and we can also see it predicts the same.
We're going to be, our main test will be using the C510. It's one of the most common standards in this case, and it's a relatively small data set, which is mostly used on implementations on the hardware language. And then our timeline, typically we plan to get the pre-processing and image data ready and figure out how to feed it into VHDL by near the beginning of March. And then we'll be doing the Python implementation near the end of March, and we should have the VHDL and the Python data ready to present by April 15th. Bramsh and I will be working on the pre-processing of the data. Bramsh and Shreyas will be doing the Python implementation, and then Shreyas and I will be doing the VHDL. These are some other references. And then any questions?
First of all, who made the background slides? They are very good. At least you understand, the activation and the weight binarizations. You know the relationship between them. Second, and of course the XNOR and the pop counting units are very important in this project. But also you need to pay more attention on the activation part and the binarization part. So how to convert a floating point number to the binary number 1 or 0. So how to do the computation. And also most binarized neural network rely on so-called batch normalization. And you also need to implement a batch normalization. I think these type of projects are really good because you can actually break down all the components. You have XNOR XNOR unit, pop counting unit, batch normalization unit, and maybe binarization unit. You have different components. I don't expect you can, make all the units here and connect them together and they work very well. I don't expect that. But you can actually partially implement some of them, and then you still can get very, very good result. For example, if you don't have the batch normalization unit, the neural network still can work, but the accuracy may be low, but still you have reasonable results. Okay.
Thank you.
Thank you.